So, I'm going to talk to you about a family of languages, of a particular type of languages called relational languages. The family of languages that I'm going to talk to you about is the ukanren family of languages. Ukanren is a Japanese word that means relation, hence the style of the language. For people that don't know what relational programming means, relational programming is a style of programming that is very, very similar to that of logic programming. You might be familiar with the language called Prolog, which is one of the most famous logic programming languages. The difference between relational paradigm and logic paradigm is very, very subtle. And some might say that it's just a linguistic difference, it's just a different name for the same thing. But the way that the author of Mini-Ukanren, which is the most popular dialect of the Ukanren family, describes it is that relational programming is essentially logic programming, but without any extra logical or impure operations. So what tends to happen in languages like Prolog is that the search space becomes so big that users usually use constructs like cut, which is a construct to trim down the search space, which is inherently extra logical. And the problem with extra logical operators is that they don't make the program that you're trying to express in a purely declarative style declarative. And it causes the way that you talk about these programs to be less powerful than otherwise it would be if you stuck with a purely logical style of programming. So this here is a very simple example of what Mini-Ukanren looks like. And this code example is essentially saying for any q and for any x and z, solve those three constraints. And those constraints are that x and z are equal, that z is equal to 3, and that q is equal to x. And give me a list of results for the possible value that q might have in those constraints. So we can clearly see that the only possible value that q might have in this set of constraints is 3, because x is equal to z and z is equal to 3, hence q is equal to 3. If you start looking into Ukanren languages, you're gonna find a lot of different dialects, and it can be a bit confusing to figure out why there's so many and what the difference between them are. So I've tried to summarize a bit the main dialects of the language of the family here. So Ukanren was the first implementation, and it was implemented sometime around 2003-2004 by Oleg Kizadov and Dan Friedman. And it was quite big, and it was quite powerful, very close to Prolog in the number of features that it supported. Sometime later, around 2005-2006, there was a book called The Resonance Schemer, written by Dan Friedman, Oleg again, and Will Bird. And that book used a very reduced, a very minimal version of Ukanren that was suitable for teaching, hence the name Mini-Ukanren. A bunch of other variations of Mini-Ukanren came out around 2009-2010. So we have C-Ukanren, which is Mini-Ukanren, but with support for constraints over finite domains. So stuff like is x bigger than 10. Then we have Alpha-Ukanren, which is Mini-Ukanren extended with capabilities for nominal logic, which is a concept that turns to be quite useful when implementing stuff like theorem provers. We then have R-Ukanren, which is the most different of all the Mini-Ukanrens, in that it doesn't really support a different feature set, but it changes completely the search strategy that the language uses to solve the constraints. And mini-ukanren and all the ukanrens until then used finite breadth first search, while ukanren is just a guided search, so it can kind of assign weights to the different paths to traverse of the state space. And finally, we have micro-ukanren. Micro-ukanren was developed in 2013, and micro-ukanren is supposed to be an even more minimalistic version of mini-ukanren. Completely pure, purely functional, and almost devoid of any macros. That I forgot to say, all those languages are implemented in Scheme. And Scheme, if you guys know it, is famous for its abuse of macros. What they did with micro-ukanren was to take all the macros away, so that you end up having a very small kernel of a language that you can just port to any other language that you want, because they don't need features that only Lisp or Scheme supports. And finally, a special mention to a library called Core Logic, which is not in Scheme, but in another Lisp called Closure. And it's arguably the most widely used variation of mini-ukanren. And it's the version of mini-ukanren that's used in quite a big amount of tools. And it kind of evolved from mini-ukanren, and it supports a lot of features that mini-ukanren doesn't, and it's got a lot of optimization that mini-ukanren doesn't. So it's, while mini-ukanren might be a research language, Core Logic is the industry version of it. I think of it that way at least. So some example of what you might use a ukanren or a relational language for. We have Barneyman, which is a research editor that the author of mini-ukanren is working on. And the interesting part of Barneyman is that it's not only an editor, but it uses an implementation of the Scheme language implemented in mini-ukanren itself to perform program synthesis as you're typing. So the idea is that you have an editor like this, where you start defining your functions here, and you provide some hints to the evaluator, like test cases, like you would do TDD. And the editor starts to populate the definition, the partial definition of your append functions, kind of inferring what the body of it might be from the test cases that you wrote. So you define the tests, and the editor tries to figure out what the definition of the function might be that make those tests pass, which is really, really cool. We have, in Closure, we have a library called Espresso, which is a library for symbolic manipulation of algebraic expressions. And the way that it looks is kind of like this, and it's not too dissimilar to what I've shown you before of pure mini-ukanren, but it's just purely algebraic, and it allows you to express algebraic constraints very declaratively. We also have a qubit, which is a linter, which can analyze your source code and suggest better ways of writing your code. So an example of a rule written in qubits would be this, where you define the pattern not equal followed by any amount of arguments, and you substitute it with the function not equal, which kind of collapses the two functions together. And as you can see, both of those examples are completely declarative. They don't describe how you would traverse code. They don't describe anything, just what you want to happen. And a final example is Odin. Odin is an engine for querying and data transformation written in Closure, using a variation of micro-ukanren. And yeah, it does data transformation and querying in a purely declarative way. You don't have to understand what this snippet does, but it's just to show you that this is querying all the values of a map. And in this statement, there is nothing that says I'm taking a map and I want to extract the values. This is purely declarative. So, I told you that micro-ukanren was a very, very minimal core, but just how small it is mind-blowing. As you can see from this introduction, the authors describe how mini-ukanren was a 2065-line program. And they found out that in this very 2065 lines for a language implementation, it's quite small, already. But they found that in those 265 lines, there was an even smaller kernel that they could extract. And that kernel ended up being just 35 lines of scheme. And in those 35 lines of scheme, they've implemented a small algebra and a small kernel for a declarative language that with the appropriate extensions can have the same power as a full-blown Prolog interpreter. So what I'm going to do today is I'm going to take you over that implementation, and I'm going to describe how it works. As I said, the ukanren family of languages is usually implementing the scheme, and the paper that I've based this talk on is implements this in scheme. But I'm aware that not all of you might know scheme, so I picked Python instead as a language that's close enough. With a warning that I don't know how to write Python, so this is essentially scheme with parentheses on the wrong side. So let's start here. We first need to define a couple of helper functions that we have in scheme that we don't have in Python. So we define here two functions. One that takes an argument and returns. In this case, it returns a frozen set, but we don't really care what this function var returns. We only care that given a unique identifier, it returns an object which is comparable with itself. And we chosen a set just as any type of wrapper, because Python doesn't have the ability to define your own types. So we're using a set as a kind of a carded type. This is a technique that scheme people use quite a bit. Is var just tests whether the input arguments is indeed a var, in this case just a frozen set. Then we need to define, so Python has lists, but it doesn't have cons cells. If you don't know what a cons cell is, it's a pair of head and tail. And you can construct a list from cons cell by just nesting consoles. So you can think of this as the list one with the list of two arguments, the list of 1 and 2. And in this case, we use none as the terminator argument. So when the second argument to our tuple is none, we know that we've reached the end of the list. The advantage of using consts over lists is that with consts you can define impure lists. So lists where the tail argument is not a list itself. Like, for example, this, which isn't representable as a list. It doesn't make sense for a list to have the first argument equal to 1 and the rest of the arguments equal to 2, because 2 is not a list. But it turns out that it's quite useful for us to be able to represent constants. And we'll see why later. And we have just helper functions to extract the first arguments of the console using head, and the tail using tail. And this comes just to test whether an input argument is a console. Finally, we have extend, which just takes a Python dictionary makes a copy of it and inserts a new key into it. This is because we kind of need immutable data structures, and Python doesn't really have them. So, with that said, the first thing that we need to define is a resolve function. So this function takes a dictionary, and it takes a term. A term can be either a var or any constant argument, so a string or an integer. And what this function does is it checks whether the term passed to it is a var. And if it is a var, do we see that var in the substitution map? If we do, then we get the value associated with that var, and we repeatedly try to resolve it. If the term isn't a var, or if it is a var but we don't have it associated in the substitution map, then we just return it. So the way that this works is, suppose that we have a substitution map that maps the var identified by 1 to the var identified by 2, and then the var identified by 2 to the constant 3. We want resolve of that var to return 3. And this is exactly what it does. With this resolve function, one thing I forgot to say is that all the different papers that describe different kernel languages have very similar operators, but often with different names, which is kind of confusing when you try to read the literature. So what I've done here is I've put on a comment the names that the paper that I'm citing uses, and I'm using different names that I picked from one of the latest papers, which I think make much more sense than the one used in this one paper. Right, so with resolve in mind, the heart of every logical programming language is unification. So we need to implement unification for a language, and unification takes two terms, the two terms that we want to try to unify with themselves, and a substitution map, which is the same substitution map that we saw used in resolve, which holds the association between a var and a value that we've already seen. Importantly, we represent unification failure as an empty, as a nil substitution map. So this function, the first thing that we need to check is the substitution map that we pass to this function nil? If so, we know that some previous unification has failed, and we must fail as well. If it isn't, then we want to resolve the term 1 and term 2 to the ground value. In other words, we want to try to resolve as much as possible of both terms, so that we have a concrete value to compare them to. Once we resolve them, we check whether they're both var and they're both equal. If that's the case, then we have nothing to do, and we just return the substitution map as we have it. If just the first term is a var, then we extend the substitution map with a mapping from the first var to the second. Conversely, if the first term is a constant and the second term is a var, then we extend the substitution map with a mapping of the second term, which is a var, to the first term, which is a constant. And we also want to, so this is all fine, but this only deals with singleton, either values or vars. We want to extend this language to be able to work with a collection of values, a collection of constraints. So we need to also test whether the term 1 and term 2 are lists. And if they are, then we just try to unify the head of the first list with the head of the second list, and recursively we try to unify every tail of the first list with every tail of the second list. If term 1 and term 2 are neither vars nor lists, then we check whether they're equal, and if they're equal, we just return the substitution map. And if they're not, this is the same as if there was a return on here. So it's a failure.
The only relation you have here is equality.
Yes, yes. So yeah, this is a very minimal kernel with only 4 type of relations available, and I'm going to describe which ones shortly. But we don't have this equality; we only have equality. So to show you how this works, taking the same substitution map that we had before, var1 mapping to var2 and var2 mapping to the constant 3. If we try to unify the var1 with 3, we should get a substitution map back, which is telling us that the unification was a success. But if we try to unify var1 with 4, then we don't get anything back, which is telling us that the unification has failed, because var1, we see here, if we try to do it in our heads, var1 unifies with var2, and var2 unifies with 3, but 3 is not equal to 4, so the unification fails. So we have this basic unification description. We need to start defining calls or relations. And the way that we do that is by creating call constructors. So a call constructor is a function from any number of arguments that you want to a function that takes a state and returns a stream of states. And we define a state as a tuple of a substitution map and an integer, which we will use to create new vars. And a stream as just a list of states. When I say just list, this is quite incorrect, but it is true for now, and we're going to see later why a string is not just a list. But for now, you can think of a string as a list. So we have the empty state, which has an empty substitution map, and the var index at 0 because we don't have any vars created. We have a utility function called newString, which takes a state and just returns a list with just that state in. We have a helper function called callGoal that takes a goal and invokes it with the empty state. And finally, we have our first goal. And the first goal here is the equality goal. So what this goal does is it takes 2 terms, and it returns an anonymous function that takes the state, as we described. And it tries to unify term 1 and term 2 in the substitution map of the states. Remember that the state is a tuple of substitution map and integer, so the substitution map in the state is the first argument. And if the if the unification succeeds, then we return a stream of the substitution map that the unification returned, and the same index, because we haven't created a new var. And if it doesn't, just remember that Python has an implicit else return none. So if this if fails, then we just return failure, which is the null value. It works by invoking this very simple goal. So what this is saying is invoke the goal equal var1 with 1, and we see that this returns a list where the state here is the first element, And it's a substitution map of the var 1 to the element 1, indicating that this equality constraint has succeeded. Creating vars manually is quite tedious, and we don't want to do this. We want a way to label vars. So the next call that we define is called call fresh. And the only thing that this call does is it just takes a relation as an argument, and it returns a call that invokes that relation using a fresh var that we just created using the index from the state, and returns a state where the index is just incremented by 1, because we've taken that numeric index for the var that we just created. I've added 2 more variants of call fresh, which are call fresh 2 and call fresh 3, which, as the name suggests, introduce 2 fresh variables and 3 fresh variables. In Scheme we don't need this because we can hide this behind a macro. In Python we don't have a macro, so we need this variation. But just think of those 2 functions as the same call as call fresh. And we can see that same invocation as before using call fresh rather than creating the var manually. And how this works is call fresh invokes this function, and Q in this anonymous function holds the newly created var. And everything else is essentially the same as the previous example that I showed you. So this is all fine, but the goals that I've described to you until now just deal with equality and introduction of new variables. They're not really interesting. You can't really do that many interesting stuff with it. So the remaining 2 goals that micro-ukanren uses are logical disjunction and logical conjunction. And to implement those, we need 2 helper function. We need an append function that takes a stream, that takes 2 streams and appends 1 string to the end of the other. This is, at the moment, this implementation is literally the same implementation as this concatenation. But we're gonna see why there is an m plus in the name rather than concat, for example. And we also need this mapend function that takes a call and a stream and applies that call to every value in the stream. You can think of it as, I don't know if your language has a mapcat or concat map. This is essentially that function. And with append and mapend, we can define those 2 goals. So this junction goal, which we call either, is a goal that takes 2 goals and return a stream which succeeds if either one of the 2 goals succeeds. And the way that we implement this is by returning a new goal that appends the stream returned by invoking the first goal over the state to the stream returned by invoking the second goal to the state. Conjunction is implemented as a mapping operation. So when we want a stream to succeed, when we want 2 goals to succeed only, the combination of 2 goals to succeed only if both goals succeed, we execute the first goal over the state, and then we map the second goal over the stream returned by the first one. So once we have that defined, we can kind of see an example of using those 2 goals. So this first relation is saying, given an arbitrary Q, if we want this invocation to succeed, if either Q is equal to 23 or Q is equal to 42. And if we execute it, we see that we return a stream where the var1 is bound to the value 23, and a second state where the var0 is bound to 42. And in this case, the var0 is our q, and we're going to later define a few helper functions to make this output a bit more pretty. We can see how conjunction works by defining a goal that says we want to return success if both q is equal to 24, to 23, and to 42. And we can clearly see that this doesn't return a string because there is never a value that is equal to both 23 and 42. For example, that succeeds is a relation where we want to say q has to be both equal to 23 and 23 itself. And if we try to invoke that, then we get a string where the var0 is correctly bound to just 23. So we have defined 4 goals at the moment. We have defined logical disjunction and conjunction, we have defined equality, and we have defined a goal that introduces fresh words. This is it. This is the kernel of microcannon. This is what just everything that's necessary to implement our logic engine. Clearly, this isn't enough for a decent UI, for a decent front end of a language. But we're going to try to create a better one now. So, the way that we defined those goals has some issues. And the reason is that a lot of relational programs, a lot of logic programs have this property of divergence. So it's really, really easy to, and often unavoidable, to define logic programs where trying to get at the value of a constraint results in infinite computation. And a stupid example of this is here. So we have a goal called 5s, which a goal constructor called 5s, which returns a goal that succeeds if x is equal to 5, or if the invocation of the 5s relationship succeeds. So you can clearly see how this has an infinite recursion in it. And the way that we invoke this is just not going to work. It's going to cause a recursion, an infinite recursion. It's really important for us that we are able to compute results even in the presence of unbound computation. And the way that we do that is by using a very, very neat and interesting trick developed by Oleg, which is by using, rather than simple lists, by using strings. And those strings are implemented essentially as lists of either concrete values or thumbs, whose invocation is going to produce a value. Thumbs or anonymous function, whatever you want to call it. So we redefine our append and mappend functions just to have this extra clause. So this extra clause tests whether the first argument is not a concrete value, but if it is a function. And if it is a function, then rather than appending the two strings together, we return a new thunk whose evaluation result is the concatenation of invoking this thunk and the second string. And similarly, we do the same thing for mappend. So we test whether the string that we're trying to apply a goal to is not a concrete value, but it's a thunk. And if it is, then we just return a new thunk whose result is the mappend of the invocation of this string to the goal. So this is fine, but this is not enough because we've defined a way to consume strings, but we're still not constructing strings, we're still operating on lists. And the way that we construct strings is by introducing this new goal, which I've called yield, and in the original paper it's called ZZZ. And it's not a function in the original paper, but it's a macro. And we don't have macros in Python, we don't have macros in many languages, so I've just defined it as a function. This call takes a goal function and the arguments to that goal, and it returns a new goal with this function barrier applied to it. So a normal wrapping goal would not return that wrapping function. By returning a thunk rather than the concrete invocation of that goal, we wrap that in that thunk that we can then match in those two branches of append and append. And the way that we use this is our fives code that we had defined before. The only thing that we need to change is rather than invoking 5 directly, we yield the invocation of 5s through this yield goal. And what this does is it produces a list, a string, where the first argument is a mapping, the unification of this var x to the value 5. And the second argument is not a concrete value, but it's a thunk representing the continuation, the remaining possible solutions for this goal. We can't really, we want to see what's in this thunk, and the way that we do this is by invoking tail on it. Tail. So we get the function, and then we just invoke it. And we invoke it again because that function, right, so invoking that function returns a new string whose first value is again a mapping of the var 0 to 5 and a new thunk representing the rest of the computation. If we were to evaluate all the thunks in the tail position, we would get an infinite string of those results. And so we're almost there. But clearly this interface is not good. We don't want to manually invoke all the thunks. So we define a helper function called pool, which recursively tries to test whether an input argument is a thunk, and if it is, it invokes it and it pulls again, because we could have the case where we have a thunk of a thunk of a thunk of potentially infinite number of nested thunks, and this is used to resolve them. And if it isn't, we just return, it's already a concrete value, so we just return that concrete value from the string. And then we have take, which just traverses the stream, invoking pool on every argument of this string. And so the interface that we would use here is, here we have the same goal as before, but we want to take 3 solutions to this goal. So we invoke take 3, and we see that we get a stream of 3 identical unification results. But we could invoke it with any number that we want. This is an infinite builder of the value 5, essentially. Let's try to define a slightly more interesting goal. So we defined a goal called 6s, which is identical to the goal called 5s, but just unifies with 6 rather than 5. And then we want to invoke a goal which succeeds if either the goal 5s, if either applying the goal 5s this fresh value x succeeds, or if applying the goal 6 succeeds. And so, if we try to do this, we see that we don't get a very interesting results back. We get an infinite string that will always ever produce 5, because we're concatenating 2 infinite strings, and so we're never going to finish consuming the first string before we reach this string, which unifies with 6. But this is kind of a problem, because when we define our programs in ukanren, we are interested in kind of getting a sample of all the possible branching that can succeed. We don't just want getting values from the same branch. And so this is one of the coolest tricks that I've ever seen in a paper. The way to make this work is to redefine append with just one line change. So before the case where we had a func appended the invocation of string 1 to string 2, just swap the arguments. So before fully realizing an entry in this string, we just swap them around. We kind of have this cooperative scheduling where after doing one computational step in one of the goals, we kind of give control back to the remaining goals. And so this allows us, this simple change allows us to get a complete, to do a complete search over the search space. If we try to take 10, we see that we have an alternating production of either unification to 5 or unification to 6. And this is, to me, this is pretty fundamental, because this is telling us that at the core of this relational language, there is nothing but a very small algebra for composition of goals and a cooperative scheduler in charge of unifying and resolving those goals. That's all there is to it. Let's try to define a couple of more helper goals using just the base goals that we define. So we define any as just taking any number of goals and applying disjunction over them. So this is just the same function as either, but it just takes any number of goals rather than just 2. Then we have all, which is the same function but for logical conjunction. So this goal takes any number of goals and it returns a new goal, which succeeds if any of the goal succeeds. And we also define a helper, another helper goal, which kind of combines those 2 goals together. So this cond goal takes a list of goals, and it combines the inner list using logical conjunction and the outer list using logical disjunction. So, and as a concrete example of what this means is, here we have a relation that says succeeds if either x succeeds for the relation 5s and 6s, or if it succeeds with 6s. And intuitively, we can see that this first relation will never succeed, because we're asking, is there a value for x such that x is equal to 5 or 6? And here we're just asking whether x unifies with 6. So with this invocation, we get this string of just the value 6. And the interesting part is that, again, this first goal is never terminating. We cannot say that it will never. We cannot say a priori that it will never succeed. So we have to test every possible unification on the string that both the 5s and goal and the 6s goal produce. But because of that use of strings, even if this never terminates, this one will terminate, and then because they cannot proceed in lockstep, we always get finite values of it. And so, with all those combinations in mind, I'm going to show you one of the coolest version of list concatenation that you'll never see. So, this is a function that takes 3 lists. It takes this is a relation, sorry. It takes 2 lists whose concatenation is the result out. And the way that this works is we say, if the first list is empty, then the result of concatenating the first and the second list must be the second list. Otherwise, if the first list is not empty, but it's itself a list, then the concatenation of that list is recursively the append of the first argument of this list to this newly created rest list, and this rest list is the output of concatenating the tail of the first list to the second list. This is a bit opaque to see. It's much clearer in scheme because it closely matches the actual definition of concat in scheme. But it's close enough to a definition of concat that we might write in a functional language anyway. And we can ask microcanner, suppose that the first list is the list with the element 1, and the second list is the list with the element 2. What is the result of this concatenation? And we get the response, not really readable, but this says that the result should be a list. I'll make this bigger so you can see it. Sorry. So here it's the result. So this is saying so we have the results in the variable number 0, and this is saying that the result of this concatenation is the list of the var 1, which resolves to 1, and the var 3, which resolves to the list 2 and none. So, kind of putting this all together in our minds, this is saying that the result is the list 1 and 2, which closely matches what we asked for. Again, this is not a very readable output. So the final step that we're going to do is we're going to try to convert that output in something that we can actually read. And to do that, we're going to define this deep resolve function, which just performs term resolution as using that resolve function that we saw in the first slide, and recursively resolves every term in a list. And we have this function reify that just causes the state to be resolved over the first var. And then we have a run function that takes a number of results that we're going to get back and a goal, and invokes that goal and reifies it doing this deep resolution. This is implementation details of a front end of microcannon. It's not really important. But with this defined, we can see that same goal invoked through run rather than manually. We can see that we get a string which is more easily readable. So we get the result that the concatenation of the list with the element 1 with the list of the element 2 is the list 1 and 2. But remember how I said earlier that with logic programming, with relational programming, the very interesting parts of relational programming is that because it's completely pure, we have a specification of a program that we can run in any direction that we want, essentially. So something that we can ask microkernel is, given the list of the element 1, what is the list that concatenated to this one would produce the list 1 and 2? And if we try to ask that, then we get the list 2 back, because we know that concatenating this with the element 1 and the list with the element 2 produces the list of 1 and 2. But even cooler is if we ask them, if we ask it, say we know that the result of a particular concatenation is the list 1 and 2, but we don't know what the input arguments are. And so this is what we're saying is, for any Q who's our result, and for any arbitrary A and B, we solve a goal where the result, the concatenation of A and B produces the list 1 and 2. And if we try to execute this, and we ask microkernel for 3 values, we get 3 different values, and it tells us that to get the list 1 and 2, we could either be concatenating the empty list with the list 1 and 2, we could be concatenating the list with the element 1 to the list with the element 2, or we could be concatenating the list 1, 2 with the empty list.
Does this terminate after 3 responses, or what happens if you try and take 4?
It just returns 3, because there's no more possible solutions. So yeah, this is everything that the paper describes. This is the small microkernel kernel plus the interface for kind of getting a better user experience using it. The full code for this is just 169 lines, but the scheme version is 58 lines. And as they promised, if we take all the new lines away, that's 35 lines. If you're interested in if you're interested in learning more about ukanrens, those are some very, very easy to read references, some very easy to read papers. And something that I would highly recommend is this one in particular. It's the dissertation that Wilbert made on ukanren, and it's 200 lines, 200 pages or something close to that. But it's incredibly well written. It's really, really easy to follow. And yeah, as you can see from the dates, the first publication of ukanrens was in 2004, but research continues to happen, and new ukanrens continue to exist. And the reason why we have so many dialects of ukanrens is that they all implement feature sets that are not compatible to each other, so different logics that don't play well together. But the rationale for microkernel is to create a kernel, a very small kernel, where you can implement those different logics on top of it. So like a common lingua franca for kernel languages. So yeah, that's all I had. I'm gonna publish the code and slides in my GitHub if you want to read it. If you have questions, we don't have much time.